Now we will learn some easy relationship of some other molecule with beta D glucopyranose. उससे पहले आपको बीटा डी ग्लूकोपायरानोज का स्ट्रक्चर मालूम होना पड़ेगा. तो चलिए, आई एम ड्राइंग द स्ट्रक्चर ऑफ beta D glucopyranose. I hope you all know the structure in chair form. In case of beta D glucopyranose, all the OH groups are in the equatorial position. This will be oxygen, this will be equatorial OH, here this one equatorial OH, this one, and this will be equatorial CH2OH. सो ये हो गया आपका बीटा डी ग्लूकोपायरानोज का चेयर फॉर्म. दिस इज वेरी मच स्टेबल बिकॉज ऑल हाइड्रोक्सिल ग्रुप्स आर इन इक्वेटोरियल पोजिशन. This is your beta D glucopyranose. Now you have to get beta D mannopyranose from beta D glucopyranose. So उसके लिए आपको just C2 एपीमर लेना पड़ेगा. That means you have to just change the position of the C2OH. In case of beta D glucopyranose, the hydroxyl group was in equatorial in the C2, but in mannopyranose, this hydroxyl group will be in the axial position. So this is the C2 epimer of beta D glucopyranose. Similarly, beta D galactopyranose is the C4 epimer of beta D glucopyranose. उसका मतलब है आपको ये C4 हाइड्रोक्सिल ग्रुप का पोजीशन चेंज करना पड़ेगा. That's why it was in equatorial position and you have to take it in axial position in case of beta D galactopyranose. Now in case of beta D allopyranose, you have to take C13 diastereomer. That means you have to change the position of OH, which is on the 1 and 3 position. So both of them were in equatorial. So in case of allopyranose, both of them will be in the axial. C1 is in the axial, C3 in the equatorial. I think you all know that which positions are the axial and which are the equatorial, but still I am just saying, if this is your cyclic form, cyclohexane, so this one is the axial up, these two are axial down, these two are axial up, and this one is the axial down. And in case of equatorial ones, this one is equatorial down, these two are equatorial up, these two are equatorial down, and this one is equatorial up. So this is your chair form, where all the blue bonds are axial bonds and the red bonds are equatorial bonds. Now in case of beta D gulopyranose, you have to take C34 diastereomer. That means you have to change the positions of OH which are on the carbon 3 and carbon 4. So you have to take them in the axial positions. So this one is the carbon 4 and this one is the carbon 3 OH. This is the beta D gulopyranose. This one is the beta D gulopyranose. But if you want to take beta L gulopyranose, that means you are just changing from D to L. For that you have to take the mirror image. If you take this mirror image, you will get beta L gulopyranose. Hudson's lactone rule. Hudson studied the rotation of the lactones derived from the aldonic acids. Using the usual projection formula, the lactone ring will be on the right or left according as the hydroxyl group on carbon is on the right or left. From an examination of 24 lactones derived from aldonic acids, Hudson concluded that if the lactone ring was on the right, the compound was dextrorotatory, and if the ring was on the left, then the compound was levorotatory. Now see, if this lactone ring is in the right of your projection, then Hudson studied that the compound will be dextrorotatory. And if this lactone ring is in the left means in the left of this plane, that then the compound will be levorotatory. He studied on 24 compounds and he found this similarity. Now Hudson's isorotation rules. Hudson applied the rule of optical superposition to carbohydrate chemistry, and his first application was to the problem of the configuration of C1 in the anomers of aldoses. Hudson pointed out that the only structural difference between the alpha and beta anomers of sugars and glycosides is the configuration of C1, thus representing the rotation of this terminal group as A and that of the rest of the molecule as B, and then taking the alpha anomer as the one with the higher positive rotation, we have this. That means we are taking the optical rotation of this portion of the alpha anomer as A. So the optical rotation for this portion of the beta anomer will be just inverse of it, minus A, because this OR was in right hand and here the OR is in the left hand. So if this was plus A, this will be minus A, and the entire molecule have the optical rotation, not entire, that means the rest of the molecule have optical rotation plus B. So this will be similar for the alpha and also for the beta, because there is no change. The only change is in the anomeric carbon. So molecular rotation of the alpha anomer, so the total molecular rotation for this alpha anomer will be A plus B. This one will be for the alpha anomer, and for the beta anomer that will be minus A plus B, because this portion is contributing minus A and the other portion is contributing plus B. So these two are the total molecular rotation. Thus in every pair of alpha and beta anomers the following rules will hold. Rule 1, the sum of the molecular rotations, that is 2b. If you take the sum, this will come out to be 2b, because this plus A and minus A will be cancelled out. So the sum of the molecular rotation 2b will be a constant value characteristic of a particular sugar and independent of the nature of R. That means this sum 2b doesn't depend on the nature of R. This R, it doesn't depend on the R. Rule 2, the difference of the molecular rotations 2a. If you take the difference, if you take this minus this, so you will get 2a, and that will be a constant value which is the characteristic of R. So the difference of molecular rotation will be characteristic of R, and the summation of the characteristic rotation of alpha anomer and beta anomer will be a constant value. So this is the Hudson's isorotation rule. Methods for determining the size of the sugar ring. Purdy's method. The sugar is first converted into the corresponding methyl glycoside using methanol and hydrochloric acid, and this is then heated with methyl iodide in the presence of dry silver oxide. So what Purdy did? Purdy first converted it into methyl glycoside. He has used methanol and HCl to make this methyl glycoside. This OH is being converted into OCH3, and then if you treat with CH3I and Ag2O, then all the rest of the hydroxyl groups will be converted into OCH3 group. Purdy's method is only applicable to glycosides and other derivatives in which the reducing group is missing or has been protected by substitution. So that's why Purdy just converted this glucose to, not glucose, this aldose to an glycoside. Methylation of a free reducing sugar by this method would result in the oxidation of that sugar by the silver oxide. In some cases, thallus hydroxide may be used instead of silver oxide. Now Haworth method. In this method, dimethyl sulfate and aqueous sodium hydroxide are added to a well-stirred sugar solution at such a rate that the liquid remains practically neutral. So what Haworth did, Haworth at first just took this pair of reagent. This base OH minus is taking up this proton at first and making it CHO minus, and that O minus is taking a methyl group from dimethyl sulfate. So finally we are getting CHOCH3. This is the Haworth method. Glycoside formation. Carbohydrate acetals are generally called glycosides. An acetal of glucose is called a glucoside, acetals of mannose are mannosides, acetals of fructose are fructosides. So this is the glucose. You are treating with methanol and HCl, then you are getting methyl alpha D glucopyranoside and methyl beta D glucopyranoside. This is the glycosidic linkage, this one. Now what is the mechanism of formation of glycoside? At first this OH is taking a proton and it is being converted into a very good leaving group OH2 plus. So this oxygen is giving its electron here in this bond and this bond is being broken. So after the elimination of water we are getting this kind of molecule, this one, where there is a double bond and oxygen is in the plus oxidation +1 state. Now this methanol will attack and it have two opportunities. It can attack either from the upside or from the downside. So if it attacks from the upside, then you will get this methyl beta D glucopyranoside, this one, because here OCH3 group is attaching at the upper position, that means in the equatorial. And if it attacks from the downside, then you will get this, and after the deprotonation you will get methyl alpha D glucopyranoside. Glycosides are stable in basic solutions because they are acetals. In acidic solutions, however, glycosides undergo hydrolysis to produce a sugar and an alcohol. The alcohol obtained by hydrolysis of a glycoside is known as aglycone. In acidic solution, glycosides show mutarotation. So this was your glycoside and you are just treating it with some acid. You are just giving a acidic medium. So this glycoside will be broken into a sugar and a alcohol. This alcohol is called aglycone. In case of salicin, this is the carbohydrate moiety up to this, and this one is the aglycone moiety. You should remember that this oxygen is of the oxygen of the alcohol, not of this sugar. Salicin is a compound found in the bark of willow trees. As early as the time of the ancient Greeks, preparations made from willow bark were used in relieving pain. Eventually, chemists isolated salicin from other plant materials and were able to show that it was responsible for the analgesic effect of the willow bark preparations. Salicin can be converted to salicylic acid, which in turn can be converted into the most widely used modern analgesic, aspirin. Now see the mechanism of the hydrolysis of a glycoside. So this is your methyl beta D glucopyranoside. So at first this oxygen will attack this proton, any one of these three, and then it will become a good leaving group CH3OH plus. So now this oxygen will donate its lone pair here and this bond will be broken. So you will get this structure, and after that water will come, and water can attack now from the upside or from the downside. So if it attacks from the upside, you will get this. When after deprotonation, you will get beta D glucopyranose. And if the water attacks from the downside here in this stage, then you will get this one, this compound, and after deprotonation you will get alpha D glucopyranose. In neutral or basic solutions, glycosides do not show mutarotation. However, if the solutions are made acidic, glycosides show mutarotation. Why? You have to explain this. The answer is because glycosides are acetals, they undergo hydrolysis in aqueous acid to form cyclic hemiacetals and then undergo mutarotation. Acetals are stable to base, and therefore in basic solution they do not show mutarotation. Now this is the structure of salicin, and this is the huge structure of doxorubicin. I don't know anything about these two. These are just only in the medicinal purpose. If you are interested, you can see further about these two. So I am just skipping this page. Reactions of carbohydrates. Monosaccharides undergo isomerization via enolates and indiols when placed in aqueous base. So if you take an open chain form of D-glucose, that will give you a D-mannose and D-fructose via this enolate and indiol structure. Now this is the mechanism. If you have the D-glucose and your medium is basic, then the OH minus will take up this proton first and it will make the carbon minus. This carbon minus is giving its electron to this bond, and this bond is being opened, the bond of the C and O, this bond. Now after this oxygen may take up a proton and you will get this type of indiol structure. Why it is indiol? Because this is a double bond in and two OH groups, that's why this is diol, indiol. Now if the base attacks here and takes up this proton, then this oxygen will become minus. Now this minus is attacking here, the bond is being opened and the carbon will be minus. This will be in equilibrium, the enolate ions. Now this can take up a proton and will become CH2OH. So you are getting a fructose. So from the glucose you are getting fructose. Because this is forming a double bond, you are getting the ketose structure. Now in case of mannose, you can also get glucose to mannose. And what is the mechanism? Similarly, this OH minus base is attacking this proton, this carbon is becoming minus, and this minus is being donated here, the electron pair, and this ring is opened, not ring actually, this bond. And now in this case, this oxygen minus, this minus is again coming here in this bond. And now there is two possibility that this bond may open from the right side and take up a proton from the right hand, then you will get the mannose. And if this bond just takes up a proton in the left hand, so OH will be in the right and you will get back the glucose. So try to understand here again, this minus, this electron pair is coming here. Now this bond have to be opened, this C double bond C, this bond have to be opened. So this may take up a proton from this right hand side. If this happens, then the hydrogen will be in the right side. The hydrogen will be in the right side and the OH group will then go in the left hand. Because this is a single bond, this can rotate. And if this bond takes up a proton from the left hand side, then this OH will be on the right hand and the hydrogen will be on the left hand. So you will get back this glucose. So if you take a basic solution of D-glucose, you will get a mixture of glucose, mannose and fructose. This is known as, a very big name. This one I can't even utter it properly. Löwbeer-Brugh-van Ekenstein rearrangement. Now in case of fructose, if you take fructose, that will also give the mixture of glucose, mannose and fructose. Now what is the mechanism? See here, the OH group is first taking up a proton. This OH is taking up a proton from here, and then this carbon is becoming minus. After that, this minus is giving its electron here. This minus is giving its electron pair here. This is and this is becoming double bond, this one. And now this oxygen is becoming free and this is becoming O minus. So this will take up another proton from here, and then this OH minus will again take up a proton from this side, and this oxygen will become O minus. Now this O minus may give it electron pair here in this bond, so this bond will be opened, this bond. And similarly, if it takes a proton from two different sides, if it takes a proton from this side, so the H will be in the left and OH will be remain on the right, so you will get the glucose. And if it takes the proton from the right side, that means this bond is being rotated, okay. and this is taking a proton from the right side. So proton is on the right, and this OH will go to the left. Then you will get the mannose. The reaction can also catalyzed by an enzyme, D-glucose 6-phosphate isomerase, and the enzyme catalyzed reaction also involves an enediol intermediate. So if you take D-glucose 6-phosphate isomerase enzyme, you will get again D-fructose 6-phosphate. Formation of ethers. Hydroxyl groups of sugars can be converted to ethers using a base and an alkyl halide by a version of the Williamson ether synthesis. Benzyl ethers are commonly used to protect hydroxyl groups in sugars. Benzyl halides are easily introduced because they are highly reactive in SN2 reactions. Sodium or potassium hydride is typically used as the base in an aprotic solvent such as DMF or DMSO. The benzyl groups can later be easily removed by hydrogenolysis using a palladium catalyst. So this is the benzyl ether formation. At first you are taking C6H5CH2Br benzyl bromide and base NaH. So this base will take up the protons, all the acidic protons. So this all will become O minus, and then the O minus will attack here in the CH2 and bromine will leave. So you will get O, then CH2, then C6H5. That means OBN. BN means the benzyl group. Now in case of cleavage, if you want to cleave the benzyl ether, just treat with hydrogen and palladium. So you will get back this glucoside. The pentamethyl derivative of glucopyranose can be synthesized by treating methyl glucoside with excess dimethyl sulfate in aqueous sodium hydroxide. Sodium hydroxide is a competent base in this case because the hydroxyl groups of monosaccharides are more acidic than those of ordinary alcohols due to the many electronegative atoms in the sugar, all of which exert electron withdrawing inductive effects on nearby hydroxyl groups. In aqueous NaOH, the hydroxyl groups are all converted to alkoxide ions, and each of these in turn reacts with dimethyl sulfate in an SN2 reaction to yield a methyl ether. The process is called exhaustive methylation. So you are taking methyl glucoside, this one, and you are treating it with some base. So this base will take up the proton, and if you just add a lot of amount of base, this will take up all the protons, and all these oxygens will become negatively charged. Then this O minus will attack this methyl group from the dimethyl sulfate, and this will convert it into OCH3, and you will get all this OH converted into OCH3. So you will get a pentamethyl derivative. Now in case of this pentamethyl derivative, if you do hydrolysis, then this OCH3, this glucoside, will be broken and you will get OH. So see here in the open chain structure, this will become aldehyde, and this will be OH. Now all of these other OH, you have converted these OH into OCH3. So this 2, 3, 4 and 6, all these positions will be OCH3. Only this first carbon will contain the CHO group, and this fifth carbon will contain a free OH group. From this you can understand that in case of glucose, this fifth OH is attacking this aldehyde group. Now see the lines. Because the C2, C3, C4 and C6 methoxy groups of the pentamethyl derivative are ethers, they are not affected by aqueous hydrolysis. To cleave them requires heating with concentrated HBr or HI. That means if you want to cleave these and if you want to get back the OH, you have to use HBr or HI, and that is concentrated HBr. The methoxyl group at C1, however, is part of an acetyl linkage, and so it is labile under the conditions of aqueous hydrolysis. Hydrolysis of the pentamethyl derivative of glucose gives evidence that the C5 oxygen was the one involved in the cyclic hemiacetal form, because in the open chain form of the product, which is in equilibrium with the cyclic hemiacetal, it is the C5 oxygen that is not methylated. From this you can say that the C5OH group is making the ring. Tert-butyl diphenyl silyl ethers show excellent regioselectivity for primary hydroxyl groups in sugars, such as at C6 in a hexopyranose. So if you take tert-butyl diphenyl silyl chloride and react with a methyl glucoside, then this will only attack the 6th position, which is the primary hydroxyl group. That's why all other positions will be unaffected, and only this OH will be converted into OTBDPS. That means you are just getting out this chlorine from, you are getting out this chloride from this tert-butyl diphenyl silyl. Now in case of this cleavage, you have to use Bu4 N plus and F minus in tetrahydrofuran. If you take this group will be removed and you will get back the free OH. Tetrabutyl amine fluoride. Triphenyl methyl chloride reacts with sugars to form triphenyl methyl ethers. These are usually known as trityl derivatives. Trityl ethers are formed much faster with primary alcoholic groups than with secondary. In case of methyl glucopyranoside, it reacts with triphenyl methyl chloride in pyridine solution to form methyl 6-trityl glucopyranoside. So if you take triphenyl methyl chloride, this will just react here because it reacts faster with the primary alcoholic groups. So you will get this structure. Beta D glucopyranoside to 2,3,4 tri-O-methyl beta D glucose. That means you have this methyl beta D glucopyranoside. You want to get this OCH3 groups in 2, 3 and 4 position. So at first you have to make a trityl derivative. First treat with PH3CCl, then this will in the pyridine solution, then this will give this, only the primary alcohol will be affected, and then take NaOH and Me2SO4. So NaOH will take all the acidic protons, all these acidic protons, and make O minus that O minus will attack the methyl group, the CH3 plus in the dimethyl sulfate. So we will get this, and after getting this, if you treat it with some dilute acid, then this group will be removed. So you will get this 2,3,4 tri-O methyl beta D glucose, and this is just the chair form, and this one is the open chain form. Paratoluene sulfonyl chloride reacts with sugars in the presence of pyridine to form tosyl esters. These esters usually produce epoxy sugars or anhydrous sugars. When hydrolyzed with sodium methoxide in the cold, if there is a free hydroxyl group on an adjacent carbon atom trans to the tosyl group, this is an example of neighboring hydroxyl group participation. So this is the structure of your paratoluene sulfonyl chloride. And now see the reaction, what is happening. If you react it with this OH, this one will form OTS. So you are taking paratoluene sulfonyl chloride in pyridine, and you will get this as OTS. Now what will happen, this OH is trans to this OTS group. So this oxygen will just attack this carbon, and this OTS group will be removed, and you will get this epoxide ring. On hydrolysis with alkali, these anhydrous sugars form a mixture of two sugars, inversion occurring at either carbon when the epoxide ring opens. So this is also called anhydrous sugar. And now if you just do the hydrolysis, if you give some base, this OH, now what are the probabilities? This OH can attack here, so this ring will be opened in case of this one. So you are adding an OH in the right hand side, this one, and this ring will be opened and take up a proton. So you will get this one after adding up a proton. And if this OH attacks from this position at the carbon 1, so this OH is attacking at carbon 1 from the right, so you will get this, and this bond is being broken, so this OH will be on the left. So you can get two structures, that means mixture of products, mixture of two sugars, this two. When the tosyl group is trans to two hydroxyl groups on adjacent carbon atoms, two anhydrous sugars are formed. At the same time, larger epoxide rings may be produced without inversion. So now see, this is the OTS group here, this one is your OTS group, and you have two OH groups in the adjacent two carbons. So both can form products. If this OH attacks, this OTS will leave, and you will get this product with inversion. And if this OH attacks, the OTS will leave, and you will get this product with inversion. But there is another one probability that this CH2OH, this OH can also attack from the upper side. If this OH attacks from the upper side, after the OTS removes, then you will get this structure which is without inversion. That means you can consider it as SN1 process, that this OTS is leaving and you are just, this oxygen is just attacking here. So this will form without inversion. Or another mechanism can be applied, that after forming this or this OH is attacking here and the ring is being opened, so you will get this structure. Conversion to esters. You have this glucose, the alpha ionomer, and you are treating with pyridine and acetic anhydride, so you will get this huge structure, pentacetate derivative. Treating a monosaccharide with excess acetic anhydride and a weak base such as pyridine or sodium acetate converts all of the hydroxyl groups including the anomeric hydroxyl to ester groups. If the reaction is carried out at a low temperature, in case at 0 degree centigrade temperature, the reaction occurs stereospecifically. The alpha ionomer gives the alpha acetate and the beta ionomer gives the beta acetate. Acetate esters are common protecting groups for carbohydrate hydroxyls. This is your glucopyranose. If you give excess acetic anhydride in the pyridine solvent, then you will get penta-O-acetyl D-glucopyranose. All these OH groups will be converted into OAC group. Now see this mechanism. First you are adding this CH3OH and H2SO4, that means you are forming glucoside. Then you are adding excess acetic anhydride and pyridine, so here you will get 4 OAC group, because at first this one is being protected by forming glucoside, so 4 OH groups are now free, so that 4 OH groups will form OAC. Conversion to cyclic acetals. If you have a diol like this and if you take acetone, this will form cyclic acetal in case of acidic solution, and the only requirement is that this diol should have to be cis, that means from the same position. This, if this is in the up position, this OH should also be in the up, and here the single bond can rotate, so there is no problem. If the 1,2-diol is attached to a ring, as in a monosaccharide, formation of the cyclic acetals occurs only when the vicinal hydroxyl groups are cis to each other. For example, alpha-D-galactopyranose reacts with acetone in the following way. Now see, in case of alpha-D-galactopyranose, as this is the alpha, so this is in the down position, because here the equatorial position is the up, and similarly this equatorial position is the down position, because in case of this carbon the axial position is the up, so these two are in the down positions, so these two hydroxyl groups are in cis position, so these two can form this cyclic acetal. You can see again, see this 2 OH, here the axial one is like this is the axial down, so this OH is in the equatorial up, so this one is the up position, and this one is the axial up, so this hydroxyl group is also in the up position, so these two vicinal OH groups are cis to each other, that's why these two also can form cyclic acetal. Isopropyridine derivatives of the monosaccharides. Sugars condense with anhydrous acetone in the presence of hydrogen chloride, sulfuric acid at room temperature to form mono and diisopropyridine derivatives. These are stable towards alkalis but are readily hydrolyzed by acids. In the diisopropyridine derivatives, one isopropyridine group is generally removed by hydrolysis more readily than the other, and thus by controlled hydrolysis it is possible to isolate the monoisopropyridine derivative. For example, Diisopropylidine, for example, diisopropylidine glucose may be hydrolysed by acetic acid to the mono derivative. This is your alpha D glucose, and you are for giving acetone in the HCl medium. So you will get this. It was your 6-member ring, but in case of glucose, this will form 5-member ring to form the diisopropylidine derivative. So from this, if you add acetic acid, this one will be hydrolyzed faster than this one. So here you are adding acetic acid, so this group will be removed and you will get this diol, and this is the monosubstituted isopropylidine derivative. Here see that one isopropylidine group is generally removed by hydrolysis more readily than the other. Similarly, if you add dimethyl sulfate in basic solution in this diisopropylidine derivative, then this free OH group will be converted into OCH3, the 3 number of OH, the OH in the third carbon. Now if you add HCl, then you will get this. These groups will be omitted. And now after that, if you add dimethyl sulfate and HCl, all these rest of the OHs will converted into OCH3. Except this anomeric OH. Actually it is in the Fischer projection. These all groups are in the Fischer projection. If you want to see the Haworth position or the chair form, start with the chair form of alpha D glucose and you can similarly see the Haworth projection. It is much more easier to understand in Haworth projection. You had this 6-member ring, you are adding acetone and HCl, you will get a 5-member ring for glucose, because this 5-member ring give you this diol, that means this cis diol. Now if you add acetic acid, then at first this group will be omitted and you will get monosubstituted isopropylidine group. And then if you add dimethyl sulfate and HCl, this free OH groups will be converted into OCH3 group. And here you are adding dimethyl sulfate and base, so this OH, the third OH, will convert it into OCH3. And now if you add HCl, if you give acidic medium, then this will be opened, this also will open, and you will get this, which will readily give you the 6-member ring. Acetone usually condenses with cis hydroxyl groups on adjacent carbon atoms, the condensation occurring in such a way as to favor the formation of the diisopropylidine derivative. For this to occur, the ring often changes size. In case of glucose, mannose, gulose, idose, 5-membered furanose ring forms, which I was telling that in case of glucose, you are starting with 6-member ring, but after adding acetone to form a diisopropylidine derivative, the ring size will be changed and you will get a 5-member ring. In case of glucose, you will get this kind of structure. In galactose, diisopropylidine derivative adopts pyranose structure. In case of galactose, there is no change in the ring size. This is the Fischer projection, that this 2OH and this 2OH will form the derivative. I have shown here the Haworth projection. I didn't have much more time to draw it, so that's why I have just done it by my own hand. I couldn't use the molecular formulas, molecular desk tools. So now see that this is your anomeric OH and this OH is in the back. So this OH can be in the up, can be in the back. So if you are taking the alpha anomer, that will be in the back. So now both of these OH are in back. So you will, these two will condense. And now see, this OH and this OH both are in the front. Even this CH2OH is also in the front, but these two will give the derivative. Fructose can form two diisopropyridine derivatives which both contain the pyranose ring. So in case of fructose, there are two possibilities. In case of fructose, these were the C double bond O, right? So now if this OH attacks from the left, this OH will be on the right, and now this OH and this OH will make the derivative. And this is the similar for both cases. This portion is the same. This 2OH group will form the derivative. But if the ring closes from the right hand side, then this OH will be on the left. Now if this OH is on the left, you had one OH here on the left, that means this OH is on the left. So now these two OH will be cis. That's why these two can condense to give the derivative. So in case of fructose, there are two possibilities. Not only does acetone condense with sugars, but so do other oxo compounds such as formaldehyde, acetaldehyde, and benzaldehyde. Benzaldehyde condenses with two cis hydroxyl groups on alternate carbon atoms of D-glucose. You are taking D-glucose and adding benzaldehyde. So in case of other acetones or any other derivatives, two adjacent carbon atoms were participating, two hydroxyl groups of adjacent carbon atom. But in case of benzaldehyde, the case is little bit different. Here you will get a 1,3 derivative. That means 1, 2 will not participate, and 3, 1 and 3 will participate in making the derivative. Just look at with methyl glucopyranoside in chair form. You can see that this OH is in the carbon 4 and this one is your carbon 5. This one is the carbon 5. This CH2 is the carbon 6. So 4 number of OH and 6 OH. The OH attached with the carbon 4 and carbon 6, they will participate in making the derivative. So this type of structure they will form. So you will get methyl 4,6-O benzylidene alpha D glucopyranoside. Now this is an exercise how to do the following transformation. Try it yourself. If you can't do, then I am just giving the answer for this problem. At first start with the beta D glucopyranose, then convert it in the 5-member ring. If you add acetone, this 6-member ring will opens up and will form a 5-member ring. Then these OH groups, this 2OH and this 2OH, which are cis to each other, they will form the propylene isopropylene derivative here and here. Now just add ruthenium tetroxide and you can just oxidize this OH. You are just oxidizing it and making it a ketone. So if you add HCl now, if you add dilute acid, so this isopropylene derivatives will be opened up and you will get back the hydroxyl groups. So this is in chair form and this is in open ring structure. So just remember this one, the ruthenium tetroxide, which can oxidize this CHOH to C double bond O. Now selective methylation of C3 hydroxyl group of D-glucose. So you have selectively methylate the C3 hydroxyl group. So for this, at first just add acetone in this glucopyranose ring. So this will form a 5-member ring and a di-isopropylene derivative here and here. Then just add Me2SO4 and NaOH, or you can also add acetic acid and methyl iodide. So this, if you add Me2SO4 and NaOH, this NaOH will take up this proton, which is the only acidic proton here, and then this O- will attack this methyl group. So you will get this OMe. Now you just give acidic medium. If you keep it in acidic medium, hydrolysis will occur and then you will get the OHs free again. So now this was your 5-member ring and this will become a 6-member ring which will remain in equilibrium. Phenyl glucopyranoside synthesis. So you are taking D-glucose and you are adding acetic anhydride and zinc chloride at 0 degree centigrade. Then all these OH will be converted into AC, all these 5 OH, including the anomeric carbons OH. Now if you add acetic acid and HBr, if you add this HBr, this bromine minus will just attach here. Actually this bromine will take the axial position due to the anomeric effect. And then if you add PHOH in silver carbonate, that means you are taking phenol. So this phenol will just make an SN2 reaction. So this phenol will attack from here. Okay, this phenol will attack from here and this bromine will leave. So you will get this OPH at the left hand side. And if you just treat it with ammonia and ethanol, then you will get phenyl beta D glucopyranoside. That means all OAC groups, all these groups will be converted into OH. Whoo, ha ha ha, uri baba, uri baba. Now come to anhydrous sugar. The anhydrous sugar is obtained when the axial CH2OH group reacts with C1, that means the anomeric carbon of beta D altropyranose, to form a cyclic acetal. Okay, so what is happening here? You are forming a cyclic acetal. But the case is that you are taking beta D altropyranose, just make the ring flip, then this CH2OH will go to the axial position and this OH will also go to the axial position. So now if you just, okay, you are giving some acid, this oxygen will give its electron here and this OH will leave. That means OH2 plus. So the deprotonation will occur. And now this OH will give its electron pair here. So ultimately this structure will be formed, and after the deprotonation you will get this anhydrous sugar, 1,6-anhydro-D alpropyranose. This is called anhydrous sugar, where this CH2OH is forming bond with this anomeric OH. Actually this is the internal conversion, where one molecule of water is just ejecting from this molecule. That's why this is called anhydrous sugar. With beta-D glucopyranose, however, it requires that all 4 OH groups become axial, and therefore the reaction must proceed through a very unstable conformation. For this reason, D-glucose requires much more drastic reaction conditions compared to D-altrose. So in case of D-glucopyranose, beta-D glucopyranose, the anhydrous sugar formation is also possible, but that requires some drastic condition, because you have to make the ring flip, which is very much unstable, because all these OH groups are in the axial positions. All these 4 OH groups are in the axial positions. That's why this is very much unstable conformation. But still, if you supply that much energy, this can form anhydrous sugar. So at first this OH will leave and this will form a double bond. Then this OH will attack here and you will get this structure. So this is the summary of reactions involving monosaccharides. Just look at this carefully. What you have learned here or what you will learn later, all of these are given here. Just a small summary.